All right, today we're going to go microscopic. We're diving deep to explore a concept that honestly makes all of our modern electronics even possible. It's called switch level modeling. And really, it's the art of seeing an entire universe of complexity as just a simple series of on-off switches.
So let's just start with the main event, the central challenge. A modern processor has billions of transistors. Every single one has to work in perfect harmony. I mean, how on earth do you even begin to design something that complex? It seems completely impossible, right?
And, it's not just about the sheer number of parts. Engineers are in this constant battle with physics itself. They have to manage all the heat so the chip doesn't literally melt. They have to shrink it down to fit into these tiny, tiny spaces. And of course, they've got to push its speed to the absolute limit. It is an incredibly delicate balancing act.
So what's the secret? Well, it isn't some superhuman ability to see all billion parts at once. The real strategy, the core idea for managing all this complexity, is something called abstraction. It's all about choosing the right level of detail for the problem you're trying to solve at that moment. A great way to picture this is with a ladder of abstraction. Think of it like looking at a map of a city. You can see the entire city plan from way up high. Then you can zoom into a single neighborhood. Or you can zoom all the way in and focus on the individual bricks of just one building. Each view is useful, but for totally different reasons. In chip design, that ladder looks a lot like this. At the very top, you've got the register transfer level, or RTL. That's the big picture, how data is moving around. Take one step down, and you're at the gate level, where we see the basic logic gates, your ands, ors, and nuts. And then, at the very foundation, we have the switch level. This is where we get down to the actual individual transistors. And here's the really crucial difference, especially between those last two levels. The gate level is all about the what. What logical function are we trying to perform? But the switch level, that's all about the how. How are we physically building that logic out of transistors? This is the exact point where the clean digital world smacks right into messy physical reality. So, let's go. We're diving down to that foundational layer, modeling transistors as simple little switches. So what exactly is switch-level modeling? Well, it's this really clever technique where we intentionally simplify transistors down to their most basic function, being either on or off. That's it. This creates the perfect bridge between the messy, analog reality of flowing electrons and the clean, binary logic of the digital world we want to create. This quote from our source material just sums it up perfectly. At this level of abstraction, we ignore all the complex physics. We don't care about voltage curves or electron mobility, none of that stuff. All we care about is one simple question. Is the switch open or is it closed? The best way to really understand any theory is to see it in action. So let's build something. We're going to build the simplest possible logic component, an inverter or a NOT gate, using this exact switch level mindset. To build our circuit, we just need two types of switches. First up is the PMOS transistor. Think of this as our pull-up switch. It connects our output to the power source, and here's the key. It turns on when its input is 0. Its partner in crime is the NMOS transistor, our pull-down switch. It does the exact opposite. It connects our output to ground, and it turns on when its input is 1. Okay, let's get our hands dirty. First scenario. What happens when we feed a 0, a low signal, into our brand new inverter? With that input of 0, our PMOS switch, remember, it activates on a 0, bam, it closes. The NMOS switch, well, it needs a 1 to activate, so it just stays open. This creates a direct, uninterrupted path from our output straight to the power source. And the result? A 0 at the input creates a 1 at the output. Perfect. All right, you can probably guess what's next. Let's flip it. Let's see what happens when our input is a 1, a high signal. And this time, everything just flips. The PMOS switch sees the 1, so it turns off, breaking the connection to the power source. Meanwhile, the NMOS switch sees the 1 and turns on, connecting our output directly to ground. So, an input of 1 gives us an output of 0. And just like that, with two simple switches, we have a fully working inverter. So how does an engineer actually describe this in the real world? Well, this is what our inverter looks like in Verilog, which is a hardware description language. And you can see how direct it is, right? We literally declare a PMOS switch and an NMOS switch, and we connect them to power, ground, the input, and the output, exactly like the circuit we just walked through. It's a one-to-one translation. Now, our inverter example was nice and clean because the switches were a great team. They worked together. But in a really complex circuit, things can get messy. This can lead to what you might call a battle of the signals. What happens when different switches start to disagree?
So think about this. What happens if one switch tries to pull a wire high to a 1, while another switch tries to pull that exact same wire low to a 0 at the same time? Who wins that fight?
The answer lies in something called signal strength. And it really is just like a tug of war. Not all signals are created equal. In a language like Verilog, a signal can be defined as strong or weak. So if a strong signal is trying to pull a wire to 1 and some weak signal is trying to pull it to 0, well, the strong signal is going to win every single time. Ultimately, this system of signal strengths creates a clear, predictable rulebook. It allows engineers to design these unbelievably complex circuits with confidence because they know exactly how any potential conflicts are going to get resolved, and that is absolutely essential for making sure a chip behaves exactly the way it's supposed to.
Okay, let's zoom back out and talk about why this incredibly detailed, down-in-the-weeds view actually matters in the grand scheme of things. So, if you're going to remember just a few things from all this, here they are. First, switch-level modeling is that essential bridge between abstract logic and the physical hardware. Second, treating transistors as simple on-off switches lets engineers run super precise simulations of their circuits. And finally, for certain types of designs, like analog and mixed signal circuits, this low-level detail isn't just nice to have, it's absolutely critical. It's a pretty powerful idea when you stop and think about it. By taking a really complex component like a transistor and just boiling it down to a simple on-off switch, we've been able to build systems, a whole digital universe, of almost unimaginable complexity. And that leaves us with one final thought to chew on. We've pretty much mastered this world of on and off. But as transistors keep shrinking, getting down to the scale of just a handful of atoms, weird quantum effects start to take over. So the question is, will that clean, perfect digital line between a simple on and off start to blur? Well, that's a question for the next generation of engineers to figure out.